Ladies and gentlemen, in the last class we discussed the full half order. So half order means we add two bits to produce a sum and a carry output. There is no incoming carry. So this performs only half of the addition process. The incoming carry is not accounted for there. So we saw the simulation, we saw the device in Verilog. Now we see the another circuit, that is a full order circuit, wherein we add two bits and the previous carry to form a sum and a carry output. So let me start with that presentation. So the speech is organized into your learning outcomes, design of the binary full order with integrated circuit, then full order in Verilog, and the summary of what you learned. So what you will learn in this video is you will learn the theory of binary addition with a full order and design that. Then you will learn to implement it in QUCS and Verilog. Then you will appreciate the wiring diagram for full order with ICs, that is with LSI chips or MSI LSI chips. Yes. Binary full order that adds two bits, say xn and yn, that n is the nth stage of addition, and the previous carry, that is carry from the previous stage, that is cn minus 1, to produce a sum bit sn and the carry output bit cn. So that performs a full addition. The truth table looks like this. If xn, yn, cn minus 1 are here, the 3-bit patterns are there, 0 0 0 0 0 1 to 1 1 1. And this is the sum value, and this is a carry value. When it is 0 0 0, the sum is a 0 and carry is a 0 0. When it is a 0 0 1, the sum is 1 and the carry is 0. When it is 0 1 0, the sum is 1 and the carry is 0. When it is 0 1 1, it is carry is sum is 1 0 and the carry is 1, because it is 1 0. And 1 0 0, the sum is 1 and the carry is 0. 1 0 1, again the sum is 0 and the carry is 1. 1 1 0, sum is 0 and the carry is 1. 1 1 1, the result is 1 1, so the sum is 1 and the carry is 1. Now we have to implement this full order. We have to, the inputs are x, y and cn minus 1, and the outputs are sn and cn. Now I have to have, there are three variables, xn, yn and cn minus 1 at the input. So I have to have an 8 or a 3 variable Karnaugh map like this. So if I put the sum, it is 0 1 1 0 1 0 0 1. It is 0 1 1 0 1 0 0 1. Now you can see that in this schema for sum, we have 4 singles rather than on pairs or quads or anything. So if I focus on these two singles, here it is cn minus 1 is 1. So this corresponding to the min time correspond to this thing is cn minus 1 xn complement yn complement, that is cn minus 1 xn complement yn complement. Or the next time is here, it is cn minus 1 xn yn, that is cn minus 1 xn yn. So the cn minus 1 is taken out, it becomes xn complement yn complement, or xn yn. This is nothing but xn xnor yn. This is cn minus 1 xn xnor yn. And this is cn minus 1 complement and xn complement yn. This is xn complement yn, and this one is cn minus 1 complement and xn yn complement. Okay, if I take out this cn minus 1 complement, it becomes xn complement yn or xn yn complement. This is nothing but xn xor yn. So this is xn xnor yn, and you know that the two input xnor and xor are complement. So this is of the form some cn minus 1 z inverse z bar, or cn minus 1 bar z, which is nothing but cn minus 1 exclusive or xn exclusive or yn. So it becomes xn x or yn xor cn minus 1, xn xor yn xor cn minus 1. That is a sum. Now let us look at the carry. So there is a 3 input xor realizes xn yn and cn minus 1, that realizes the sum part, and now there is a carry output part, which is 0 0 0 1 0 1 1 1. So it is a 0 0 0 1 0 1 1 1. Okay, now you can see that there are 3 pairs, one in blue, the other in orange, and the other in the third one in red. So if I look at these times, if I look here, it is xn yn. For corresponding to this blue, the time is xn yn. Corresponding to this red, there is Cn minus 1 and xn, Cn minus 1 xn, and corresponding to this orange one, it is Cn minus 1 xn yn, Cn minus 1 yn, Cn minus 1 yn. So summarize, we can summarize full order with this set of equations. That is, Sn is some output is xn, yn, Cn minus 1. These are the inputs. And the output Sn is xn XOR yn XOR Cn minus 1. And the carry output, that is xn and yn, or Cn minus 1 xn or Cn minus 1 yn. Now we can realize this circuit in this figure. That is, here it's an XOR operation. X, y, Cn minus 1 are the inputs to that. That S is x, y, xn XOR yn XOR Cn minus 1. And here it is xn and yn. This is ANDed. Then xn is ANDed with Cn minus 1. Yn is ANDed with Cn minus 1. Then they are all together. All the three values A, B, C are all together to form the carry output Cn. Now I mark this as ABC because in Verilog these 3 points will appear like internal net. So there I will be using these variables. It is to make it easier that I put these variables here. So here it is A or B or C that forms my Cn. Now this full order can be simulated in QUCS. If I come here, so when I use QUCS, here what I do is I have many projects because my in the long term what I'm asking is first I will make a full order, then I will connect 4 full orders. I connect 4 full orders together to form a full order blocks to form a 4-bit parallel adder that I will put into another block. This block, this 4-bit adder block I will use for making a BCD adder that way. So it is wise to work with projects. So I use a project here. I initiate a project here and add these files to project. So this is a full order here. This is my xn, this is my yn, and this is my input Cn minus 1. Here I marked as Cn. So this block has the pins 1, 3, 5. These odd pins I marked for the input, and the even pins 2 and 4 I marked for output. 4 is the sum and 2 is the input. 1 is connected to xn, 3 is connected to yn, and 5 is connected to Cn or Cn minus 1. Now what is inside the circuit? This is developed as a sub-circuit. If you go into the sub-circuit, you can see how I developed that. So if you look here you can see that there is no simulation block here. There are no inputs or outputs. So this is something called a sub-circuit. So it is wise to work with sub-circuits. It's like writing functions in Verilog. So here 3 inputs are there, xn, yn, Cin or Cn minus 1. There are 3 input ports. These green ports are the input ports, and these red ports are the output ports. Now these pins 1, 3, 5 I reserve for my input, and these ports, this I reserve for my output. So here there is a 3 input XOR gate. This is my sum. This realizes my carry. This is x, y, this is y, c in, and this is x and c in. So this together, if you OR, this forms my carry output. Now you can see that this cannot run because there are no simulations or input or output. So what I do is I add this file to the project I created, and I drag and drop here. Or if I will now this is my full order circuit. Now here these inputs are given. Xn is 4 nanosecond, 4 nanosecond. Yn is a signal with 2 nanosecond duration, and Cn is with 1 nanosecond duration. So if I run this simulation, you can observe this waveform as well as the truth table. Here you can see that when the inputs are 0, 0, 0, output is sum is a 0, carry is a 0. 0, 0, 1, sum is a 1, carry is a 0. 0, 1, 0 again, sum is a 1, carry is a 0. 0, 1, 1, the sum is a 0 and carry is a 1. 1, 0, 0, the sum is a 1 and carry is a 0. 1, 0, 1, it is carry is 1 and the sum is 0. Here again the sum is 0 and carry is 1. When it is 1, 1, 1, it is both ones, S and carry are ones. It just repeats. Now the waveforms are similar to that. These waveforms are an representation. You can see for different patterns the sums are coming out correctly. So this is how I do the simulation in QUCS. Now I can use the LSI chips or ICs to make this circuit in one board. So probably if you can go to the lab and take some ICs and develop this circuit on breadboard or PCB. So that wiring diagram will look like this. So what I need is I need some XOR gates and AND gates and OR gates, okay, to realize this. Sum is realized by two AND gates because it is A XOR B XOR C. Here I use a 7486 IC. So what I do is I place the 7486, 7432 and 7408 on the board and ground their pin, 7th pin, ground all the 7th pins and connect to all the 14 pins to supply. And here if you say you put 3 lines X, Y, Z, this may be connected to X, Y and C. This may be connected to toggle switches which can make it either high or low. Now you can see that I use these O XOR gates. First I take this XOR gate with the input 12 and 13 and the output at 11. This is connected to the next input and here it C is given to this. Okay, Cn minus 1. Xn and Yn are given to the first XOR, that gives you X XOR Y. That is XORed with Cn minus 1. So that here at the 8th pin I get my sum. Here I connect a normally on LED through a 220 ohm resistor so that whenever sum goes low, this LED glows. Now I have to make, this is how I make my sum. And to make this carry I have to have some and input. So one is X and Y. X and Y, here I create this 12, 13, 11. This gate is one AND gate to which I connect this 12 and 13 to X and Y. Then this Y and Cn minus 1, Yn and Cn minus 1 I connect to this and that output is taken. This output is given to what? Then there is a third gate doing this. Now what happens here is here this is one output of one AND gate. This is the output of another AND gate. These are ORed. Then this is the output of the third AND gate. This is connected to this gate. This output, the output of this OR is connected to this OR, so that this circuit realizes a 3-input OR gate. Okay, this circuit realizes a 3-input OR gate. Now this is my actual carry output that is connected to an LED through normally on LED through a 220 ohm resistor. Now when if I apply 0, 0, 0 to 1, 1, 1 pattern here, these LEDs will glow depending on the condition in the truth table. So you can verify this in the lab when your turn comes. Now the next task is I have to make this full order in Verilog. So what I do is here I am in your syllabus a gate level design is given. So what I do is I go by gates. So what I do is I write a module, say F order in module F order end module, that way module F order end module. And here the output of wire is a sum, output is a sum, that's a wire, and C out, these are wires, output quantities, sum and C out. Then X, Y and C in are the input of wires. Then there are some intermediate thing. One is I am using I'm realizing this 3-input XOR as a two input XOR. So output of one XOR is connected as inter sum. So if I take here the first statement, first concurrent statement XOR N1, some name, inter sum XY means the first this input XY they are XORed to create some intermediate value or internal net inter sum. That is XORed with the Cn to get the sum. These two lines create these two are 2-input XNOR gate. These two lines create a 3-input XNOR gate. So what ultimately it does is into this 3-input gate I give X, Y and C in, and it generates the sum output. Okay. Now this these are like X, Y is ANDed together. These three ANDs create my 3 times and carry. So first one is X, Y and X and Y, that gives me A, and X and C in that gives me B. These are all AND gates. Then Y and C in gives me C. So these are the 3 times. Now we have to OR it. Again, ORing means I have to have a 3-input OR gate. Now I am realizing it with 2-input OR gates. So what I do is I give an intermediate variable a, that's a internal net d, internal net d. So ab is given to an OR gate, that gives me d. Then d is ORed with c to get my c out. Okay. The complexity comes because instead of using a single, or you can define some 3 input XOR and 3 input NOR and do that. But here I went by that diagram. So I used 2 XOR gates to make a 3 input XNOR gate and 2 OR gates to make a 3 input OR gate. And these 3 and functions, they create this things ABC. Okay. Now we can run this thing and the test bench. So let us go to that. Now here is this circuit. This is a full adder, not the VCD file. This is a full adder.v. Okay, this is just the same thing we discussed, and there is a, I generate a test bench here. Okay, there is nothing new in this test bench. Only thing is I grave include fadder.v and module test bench. These 3 are the input variables x, y and carry in that I as a register, and wire sum and carry out are wires. What I do is then I make an instance of the full adder. Then I make an instance of the full adder. What I do is fadder, some give name, some carry out. These are the outputs and these are the inputs x, y, carry in. Then I run the simulation for some time. Okay, I make a dump file called fadder.vcd. These are bit patterns given. Now if I run this code, you can appreciate this. I will make it a little bigger. Now I run Verilog. Now let us run this a.out. Here you can see that these conditions are coming in, like when xy is 0 0, carry in is 0, both the sum and carry out are 0. When it is 0 0 1, sum is 1, carry is 0. When it is 0 1 0, again sum is, carry out is 0. If it is 0 1 1, sum is 0 and carry out is 1. When 1 0 0, the sum is 1, carry out is 0. 1 0 1, the sum is 1, sum is 0, carry out is 1. And it is 1 1 0, again the sum is 0 and the carry out is 1. When it is 1 1 1, the sum is 1 and the carry out is 1. Now we can see this waveform, GTK wave. I can have this inputs x, y, carry in, then the sum, then the carry out, and I can zoom it a little. Okay, here initially for 5 nanoseconds it is indeterminate. Here from 0 to here it is a 0 0 0, the sum is a 0 and the carry is a 0. It is 0 1 0, the sum is 1 and the carry is 0. It is 0 1 1, it is a 0 1 0, it's again a 1, sum is a 1, carry is a 0. It is a 0 1 1, the sum is a 0 and carry is 1. Here it is 1 0 0, the sum is a 1 and the carry is a 0. Then it is a 1 0 1, okay, the carry is 1. Okay, carry is 1. Here again 110, again sum is 0 and the carry is and it is 111. You can see that the sum is 1 and the carry is 1. So this is how a full adder is realized in Verilog. Let me go back to the presentation. What you learned in this, you learned the theory of binary addition with the full adder, and you designed it. You understand that full adder means it adds three things: the percent input bits xn and yn, and the carry from the previous stage. It generates two output. One is the sum output, and the other is a carry output. And you designed it with three variable Karnaugh maps. Then the second point is you learn to implement the full adder in QUCS and Verilog. Then you understood the wiring diagram for full adder with ICs, that is with XOR, AND, and OR gates. And that is the end of this presentation. I thank you all.